Welcome to CMOS RF integrated circuits. Today is the 24th lecture and we were working on low noise amplifier design, and we had come up with a certain topology for a low noise amplifier, and today we are going to evaluate what is the noise performance of that particular amplifier, and following that we are going to investigate other possible LNA topologies, and we will see how far we can go with this. So, the topology of the LNA that we came up with looked something like this. Where am I? It was basically this. Okay. This was my final LNA topology. All right. Input is coming into a MOSFET, into the gate of the MOSFET. There is source degeneration through an inductor that gets amplified, that gets converted into a current. The current is converted into a voltage through a cascode MOSFET, which is placed further on, and the load is also inductive. This is done for matching purposes, output matching purposes, because eventually most probably what you are trying to drive is a capacitor, is a capacitive load. Okay. So, this was my basic topology that I started from. There are going to be other issues to look at, like biasing, etc. You can take it back to your analog circuits classes to understand biasing issues. A crude way of biasing would probably look like something like this. This is a current source, a current mirror. We want a certain current. So, this would be the way to generate a current mirror, and over here I have my inductive load and probably my final load capacitor. All that is fine. This, the top device is my second device, but my first device, if I place an inductor on the source side, nothing changes as far as DC goes, because an inductor is a short as far as DC is concerned. And I also want to place an inductor and connect it to my signal source. But if I do that, if I connect it directly to the signal source like I have done over here, then what is going to happen is that the signal source's DC voltage, which is 0 volts, is going to propagate, and as a result the gate of the MOSFET will be biased at 0 volts, which is not something that you want. So, you put a blocking capacitor over here. All right. Now, in this case also, the small signal voltage over here, because of this current source, the small signal voltage at the gate of the current mirror is 0 volts, which means that the small signal voltage at the gate of the MOSFET is 0 volts. So, it is not going to work. So, you have got to put an AC block over here. So, an AC block could be a large resistor, it could be another inductor. You try to avoid inductors, so you put a large resistor over there. So, typically this could be a very crude way of biasing things. If you want to do things better, you would optimize further and convert this current mirror into better topologies, etc., etc. This is also wasteful in terms of current. So, if you plan to have I bias flowing over here and you you put a 1:1 current mirror, then you are consuming 2x the current, right. So, probably you want I bias, a fraction of I bias, let us say I bias by 100, and you make these W by L's in the ratio of 1:100. Okay. So, this also could be done. Anyway, this is an aside. This biasing is just an aside, and this is not really the meat of our discussion. What I want to discuss today is the noise performance of this particular LNA, and as far as the noise is concerned, what I have got in my design is something like this. This is my load, this is my cascode device over here, this is small signal ground as far as the cascode is concerned, and as far as my input device is concerned, I have got an inductor connected to my input voltage source directly. I have thrown out that capacitor because hopefully it is a large capacitor which is going to make it a short. I have also thrown out the biasing resistance, the bias T that I had up front, because hopefully that resistance is so large that it looks like an open circuit. If you prefer to put an inductor there, that is also fine. So, these are called chokes, RF chokes, right, inductors that you put for biasing purposes, which look like open circuits at RF frequencies, that is an RF choke. So, this is my circuit as far as my LNA is concerned, my signal is concerned, this is what it sees. Now, when we are going to talk about noise, we have to realize that my signal has a resistance associated with it, that is number 1. Number 2 is looking in here, looking from the gate, the model for my because it is a matching network, the model for my voltage source is something else. The model for my voltage source is the appropriate input resistance and the appropriate voltage, right. So, this is what we had done in the previous class. Okay. And then I said that we need to model the noise of each of these MOSFETs. So, to model the noise, I said let us make our first approximation to make our life easy. To make our life easy, let us approximate the input impedance of the cascoded MOSFET. Looking into the source of the cascoded MOSFET, let us say that you see 0 ohms. It is very reasonable approximation, it is very reasonable. And so, what I am basically saying is that let us say that the second MOSFET is irrelevant, it usually is irrelevant. Let us say that all I have got is this, all right, and the MOSFET produces its own noise. Let us focus on the channel noise of the MOSFET. So, the channel noise of the MOSFET, I have got a mean square noise current over here, which is in addition to the channel current. All right. So, this is what we have got, and in addition to this, we should not forget that the MOSFET has its own parasitic capacitances. There is CGD, there is CGS, there is C source to bulk. Okay. C drain to bulk is irrelevant because both sides of both the drain and the body both are at ground. So, drain to bulk capacitance is not relevant as long as you have got a good ground. Okay. So, this is what we have got. Next step, I am going to delete my input voltage source completely, it is only a resistor. Okay. Now, this particular resistor will also have its own noise voltage, that is the source noise. As far as the noise figure is concerned, it is the total noise divided by the source noise, that is the noise figure. So, this also has its own noise voltage. All right. So, this is what we have got, and now we have to find out what is the channel noise when I refer it back to the input voltage source. What is the channel noise when I refer it back to RS? Okay. So, this is basically the question. In other words, what should be a voltage that I need to apply over here? So, what is V, what should Vx be such that the current over here is In? What should Vx be such that the current over there is In? If I know Vx, then Vx squared will give me In squared, right, mean squared will also correspond. Okay. So, what should be Vx such that I get so much channel current? This is the basic question. And to answer that, what you have to do, let us forget about this channel noise right now. MOSFET is noiseless, let us say the MOSFET is noiseless, I apply a voltage Vx. What should this voltage Vx be such that the current in the channel of the MOSFET is In? This is the basic question, right. And let us work it out. So, if I have Vx, then Vx is going to undergo a voltage division, input impedance looking in So, looking in from this point, I see some input impedance. That input impedance is really given by this quantity, remember. Right, of which we found that it is dominated by Gm times Ls by Cgs. The remaining two are not of terribly great consequence over here. So, the input impedance looking in over here is Gm times Ls by Cgs. It is a resistance that you see looking in over there. Now, you are basically going to do a voltage division, and that will tell you what is the voltage over here with respect to ground, but that is not enough for me. It is not enough to know what is the voltage with respect to ground. I want to know what is VGS, because when I know VGS, Gm times VGS is In, right. Now, the next thing to understand is that this current plus Gm times Vgs is this current. All right, and given these two, we can figure out what should be my VGS, what is my VGS. Okay. So, So, the first step I can figure out what is the voltage at the gate. The voltage at the gate is given by V times Gm Ls by Cgs divided by Rs plus j omega Lg plus, let us ignore CGD for convenience, let us say CGD is not relevant at all. No, CGD is necessary for matching. Okay. So, 1 by j omega CGD in shunt with Gm Ls by Cgs. This is the gate voltage. All right. Now, once you know the gate voltage, what I am saying is that it is very easy to find out what is the current going into the gate. The current going into the gate is Vx, V minus this is the current going into the gate. Of course, CGD is also part of the show over here. So, I gate, so it's very easy to compute I from this. I gate is really I times j omega 1 by j omega CGD divided by 1 by j omega CGD plus Gm Ls by Cgs. Now, this I gate, this is the gate current. This gate current is dropping across Cgs. All right, it has no other place to go. It goes across Cgs and it creates a voltage across it. So, I gate times 1 by j omega Cgs is equal to Vgs and I n is Vgs times Gm all right. So, now you know I n in terms of V. Do you know I n in terms of V? Yes, because I know V g in terms of V. If I know V g in terms of V, then I know I in terms of V. If I know I in terms of V, then I know I gate in terms of V. If I know I gate in terms of V, then I know I n in terms of V. Once I know I n in terms of V, then I can figure out what should be the V to produce I n equal to what should be V squared to produce I n squared equal to 8 by 3 k T G m d f. All right. So, this is the story. Now, you know what should be V squared. Now, that V squared plus the source noise is the total noise divided by the source noise is the noise figure. So, there are a lot of computations involved. I am not going to attempt a closed form solution for this, because it is too difficult. There are too many manipulations going on, and the closed form solution may or may not give you any real insight into what is going on over here. What you need to understand is as follows. A certain gate to source voltage is needed to have a certain current. Now, I have a matching network. I have made a matching network to make sure that looking back from the gate, I see what I see looking into the gate. So, looking into the gate, this is without CGD etc. I see GM-LS by CGS, a resistance. Remember, this is what we did. My matching network is such that looking back from here, I also will see the same resistance GM-LS by CGS, otherwise I have not got any matching. So, all of those gate inductance, CGD, all of those and RS, all of those can be lumped into one big resistor. A Thevenin equivalent of all that is one big resistor, which is called GM-LS times LS by CGS. So, this is the first thing that you need to observe. So, if that is the case, if I am going to apply a voltage over here, I will get half of that voltage over here. Right? What is my current going to be? My current is going to be V by 2 divided by GM-LS by CGS. All of this current is going into the gate, which means that it is dropping across CGS, which means that the gate to source voltage this is the gate current. This gate current is going to drop across CGS. So, VGS is so much, which means that the drain current is so much. All right, this is beautiful. I have simplified all of this nonsense into this simple understanding, okay, with the help of the matching network. Of course, now you are working at the match frequency, okay. You are not doing arbitrary frequencies. Over here omega was there, we did not know what is the value of omega, omega could be anything. This is a very general analysis, you do not have to bother about the general analysis. Let us work at the particular frequency where the LNA is going to operate. The LNA is going to operate at the match frequency, and at the match frequency this is what is going to happen. The drain current is going to be so much times the Thevenin equivalent of the voltage. All right. What is the corresponding voltage that you had to apply when to transfer the same amount of power over R s? So, to have the same amount of power as far as the source is concerned, your network looks like this. You have done a good job with matching. This is what your network looks like as far as the source is concerned, right. So, Vs and Rs, they are delivering how much power to Rs, to your load, to the LNA. Vs is delivering Vs squared by 4 Rs. This is the power delivered to the LNA. Here the power that I am getting is V by 2 squared by GM LS by CGS. Now, these two have got to be equal. So, really this 4 is going to cancel this with this 4 and Rs is going to come on the top. So, Vs squared by V squared equal to Rs times CGS by GM times Ls, right. So, Vs is equal to V times square root of all of the above. All right. It is like this. To get a certain current I n, to get a certain current I n squared, I need to apply a certain voltage for this Thevenin equivalent network. Let me try to give you the gist of this. So, to get a certain I n squared, I need to apply a noise voltage to this Thevenin equivalent of the source side network with the matching, right, and that relationship is really very straightforward. All right. Now, of course, there is a j over here, and when you square the j, it is going to give you a negative sign, but do not be bothered by it. It really has to be the absolute magnitude square of this, okay, which means the j will go away. Okay. So, this is step 1. Step 2 is to understand that to get a certain V over there, your source has to have a certain source voltage, and that relationship is given over here. Okay. This is the equivalent input referred noise voltage that you needed to apply in the first place. So, as far as your noise figure is concerned, your noise figure will be 4 kT RS df plus In squared is 8 kT gm df times RS CGS by gm Ls times 2 omega Ls whole squared divided by 4 kT RS df. So, this is the approximate noise figure, rather noise factor. Then 20 log of this will give you the noise figure. So, this is the simplified understanding of what is going on. The simplified understanding of what is going on is to operate at the match frequency. At the match frequency, if you look at the source looking back from the gate of the MOSFET, you are just going to see the same resistance that you are seeing when you look into the gate of the MOSFET, right. Of course, I have done some approximations here. What is the big approximation that I have done? The big approximation that I have done over here is that this is GMLS by CGS. It is not exactly that. It is GMLS by CGS plus a few more components plus j omega Ls plus 1 by j omega CGS, right. In which case looking back into the source should give you the conjugate of that. Okay. And appropriately you have to modify your mathematics, but it is definitely easier to solve your understanding to proceed with your understanding this way than to solve the general equations and get lost in the mathematics. So, this is what we attempted first. We tried to solve the general equations, we got really lost in the mathematics in spite of making several approximations, right. Here also I made the same approximation, which is not really precisely correct, right. And then I made several, I took several steps, I did not solve any of the steps, whereas over here I solved all the steps, I made that one same approximation, solved all the steps and I came up with a concrete result. Now, this gives you a better picture of what is going on and what needs to be done as far as your LNA is concerned to get a certain noise figure, etc. So, to get a certain noise figure you have to optimize certain parameters at a given frequency. All right. So, what can you work with over here? GM is going to cancel away. So, you can't really work with GM. LS is not something that you want to work with, LS depends on the matching properties, right. LS is not something that you want to really be working on as far as your device is concerned. It's omega is given, omega is the frequency of operation of the LNA, the frequency at which you did your matching. CGS, CGS changes when you change the device geometry. So, CGS is definitely something that you are going to work with. The larger the CGS, the more noise figure you are going, noise factor you are going to get. Okay, it is no surprise, larger the capacitance is going to be, the more noise factor you are going to experience. So, this kind of completes our understanding of the tuned low noise amplifier. So, this is how we normally design a tuned low noise amplifier. So, you start off with a certain current that has been given to you, and given the certain amount of current you figure out what should be no, given the certain amount of current you first figure out what should be the transconductance, what should be CGS of your device. Once you have figured out what is GM, what is CGS, then the rest is easy, the rest is just fitting and finding out the W by L ratio and everything else. Okay. And of course, you have to design the matching network at the input and the matching network at the output side. So, what could be other topologies for the LNA? This particular low noise amplifier that we designed, it is a very sharply tuned low noise amplifier, it is tuned at the frequency of interest. We have also done special optimizations. We have put a source degeneration inductor. It helps as far as noise is concerned, because now the resistor is artificially created and not directly created by a physical resistance over there. Okay. Other options that you might have are to use the inductance available within the channel of a MOSFET. So, the MOSFET model has a couple of things. Besides the capacitors, the MOSFET model has a gate resistance. It also has a channel inductance. Okay. So, you could use this particular property of the MOSFET model to your advantage and try to develop a matching network on the input side. So, your plan is to develop a matching network over here so that when you look into the matching network, you want to see RS. Okay. So, what I am saying is, consider the following, consider that the MOSFET is not just GM and CGS. So, the normal MOSFET model is this. Let us say that drain is at ground, small signal ground, or you are driving a small impedance with the MOSFET. So, drain is almost at ground potential. So, this is the normal MOSFET model. RDS is irrelevant over here because both sides of RDS are at ground. Small signal ground. C source to body is irrelevant because source is at ground, body is at ground. Drain to body capacitance is also irrelevant because drain is at ground, body is at ground. Okay. So, this is the regular MOSFET. Now, as far as the regular MOSFET is concerned, the input impedance is a pure capacitor, and if you have a pure capacitor as an input impedance, then you can't match it to a resistance through any matching network. It is not possible to design such a matching network. Okay. You are always going to see a capacitance, or you are always going to see something which is lossless. There is no power consumption in this, right. So, the idea is, do not think of the MOSFET as just a capacitor. It is unwise to think of the MOSFET as just a capacitor. It is not. First of all, there is gate resistance. What is gate resistance? It is not the resistance between gate and channel, it is the poly of the gate, it is a distributed resistor. You are applying contact somewhere and the charge has to spread all over the gate, and it has to go through a resistance to do so. Effectively you see an RC time constant. So, you get an effective lumped resistance value, that is the gate resistance. It is usually a very small resistance, who knows what its value is going to be, could be a couple of ohms. So, first of all there is some gate resistance. The next thing is, so as soon as you have got gate resistance, your input is no longer a plain capacitor, the input is a resistor, there is a resistive portion to the input portion of the, so your design, your gate is actually consuming power. Okay. So, you can design your matching network for this particular purpose, that is you could make sure that the power consumed by the gate is equal to the maximum power that can be delivered by that particular source. If you do so, what kind of noise figure do you expect? If you do such a thing, if you just make a matching network to match the impedance that you see over here, to RS, source resistance, what kind of noise figure do you expect to come up with finally? You expect to come up with a noise figure of around 3 dB or half, noise factor of half. Why? Because the gate resistance is going to generate noise, the amount of noise that the gate resistance is going to generate referred back to the source is going to be equal to the source noise, because you have matched the source resistance to the gate resistance. That particular ratio has already been used to design the matching network. So, it is just going to step up by the same factor, and as a result the gate noise will be equal to the source noise. So, you will get a noise factor of half right away. So, you do not even have to think about the channel. Now, you think about the channel which is going to add further noise referred back to the gate. So, the minimum noise figure that you can get out of this kind of a circuit is 3 dB. It is no good, not particularly exciting. All right. You can use bipolar junction devices. Okay. I will not confuse you, but if you do use a bipolar junction device, then you do see a base resistance, but that base resistance is not a resistor. This gate resistance is a resistor, it is coming because of the presence of a resistive gate, distributed resistance on the gate, poly is there, right, polysilicon, it is coming because of that, it generates noise, it consumes power. The gate is going to consume power and generate noise. Okay. As far as the bipolar junction device is concerned, you will see the model for the bipolar junction device transistor. Could be something like this. Okay. But this resistor that you see over here is not a real resistor. Okay. It is not really a resistance that is physically present over there, and as a result you do not expect it to generate noise like a real resistor does. So, there is a subtle difference between these two. Okay. Although the models look very similar, there is not much difference as far as the model is concerned, right. there is no difference as far as the model is concerned. Probably there is an extra there is a capacitor less in the BJT, but as far as the understanding is concerned, both are very different. In the BJT case, there is no physical resistor over there that is going to generate noise. In the MOSFET case, there is a physical resistance on the gate of the MOSFET. It is going to generate noise. It is called the gate noise, right. So, these are other possibilities. So, basically you can just have, thinking about the BJT, you could just conceive of designing something which looks like this. Right. All you need is a matching network to match the resistance that you see looking into the base emitter to the source resistance, and then the same computations follow after that. You can have a cascoded device after that. You can have a cascoded device after that. You can have anything else for further amplification. You need an output matching network. Could have something like this, right. Here this base emitter, the resistance between the base emitter is not a physical resistance, it is not going to generate its noise, all right. So, you can make low noise amplifiers with BJTs as well. MOSFETs are always preferred because if you are going to make CMOS RFICs, then you should stick to MOSFETs, and if you stick to MOSFETs, then this particular circuit is no good. That is all I am trying to say over here. This circuit over here is not going to have any benefit. Right. Why? Because looking in here you see RS, looking in here you see the gate resistance plus complex conjugate of plus the conjugate of the rest of the stuff, and the gate resistance is noisy. So, the same noise is transferred to the source. So, you get about 3 dB of noise figure right away. So, this is no good. Other variations include I can attribute some of these variations to a gentleman named Bram Nauta. Okay, you can look up several papers written by this particular gentleman, all about low noise amplifiers, noise cancellation techniques. So, he can actually cancel the noise produced by this channel by coupling it in the reverse phase into the next stage. It's not very easy to understand what is being done over there, but So, the noise current uh, by this device M1 is responsible for a certain amount of input referred noise. So, the noise current by M1 is responsible for a certain amount of input referred noise. Part of this noise current is going to decide to come from this capacitor. Part of it is of course going to be sourced through the second MOSFET, because it is a low impedance node. But if I artificially place a second capacitor over there, I can have some noise coming out in the other direction, from the other direction. Now, if I do so, then that can create a voltage that is proportional to the current with 90 degrees phase shift, right. The voltage will lag behind the current will lead the voltage, all right. So, this kind of strategy is used routinely. These are noise cancellation techniques. You can look up several papers written by this particular gentleman and further study these techniques. All right. So, I am more or less going to summarize over here. So, what we did today was basically to understand the noise of this one MOSFET. We did not even look at the second MOSFET. The noise contribution of the second MOSFET is going to be divided down by the gain of the first stage, okay, and hopefully that noise is not going to become significant. So, the significant noise contributor over here is the first MOSFET. Second MOSFET also will have its own noise contribution, but its effect is going to become much lesser. So, that is why we kind of did not even look at the second noise source. Why? What is going to happen? The second noise source, this is a noise source, right. Where is the current going to go? The current can go into this or it can go back through this. The impedance looking downwards is very high, the impedance looking upwards is very low. So, it is going to prefer to go into the low impedance node. So, as a result the voltage it develops backwards is very little. So, if it develops a low voltage across this, then it is reasonable to expect that particular noise source to contribute very little noise when you refer it back to the input. So, this is what I am trying to say, and that this is why we did not even bother analyzing the second noise source. All right. So, the first noise source, the first MOSFET, you could choose to think of it as a noise source, do the proper analysis and get lost in all of the calculations. The second approach is to have an understanding that at the matching frequency, the inductor and the capacitor, the inductors together are such that the source resistance matches with what you see looking into the gate, and with that approach we computed a noise figure. So, this is where we are going to stop. There are several other LNA topologies. I refer you to papers written by this gentleman for very good designs, very competitive designs over broadband, etc. So, please take a look at papers written by the gentleman. It is not going to be possible to cover everything in this particular course. Okay, thank you.